So apparently my brush with internet celebrity was yesterday Tuesday's lecture or something. At least it wasn't the Cloud Chaser video. Anyway, I also wanted to, let's see here, a handful of things we want to do before we get started today. Today, of course, is the so-called Big Picture lecture. It's the lecture where we take a little moment's break here and we start putting all this together. Because as hard as it is to believe, I know I've told you this already before though, there really is just sort of one thing in this unit. This is all sort of one interrelated picture about the general circulation and how the general circulation establishes jet streams and how troughs and ridges of the jet streams cause cyclones. Cyclones cause the air masses to move, the leading edges of the air masses of the front. It's all one coherent picture. So that can be a bit much for people to get right away. Now, I found this a long, long time ago. It's just a little passage from a really stupid book that I wish I could recommend, but I can't. It's from a book called The Weather Makers. There's actually several books in the world called The Weather Makers, but this particular one is by Ben Bova, and it's basically if the Hardy Boys were meteorologists. I mean, it's just sort of a lame little mystery, but they're weathermen. But they have this great explanation of general circulation in there that just is way too poetic to leave alone. Because it's just in this little bit of slightly flowery-ish prose, we get a nice description of how the general circulation works. The author writes that the sun rose brightly across the western half of the globe, its unfailing energy heating the seas and the continents. Well, that's what we did the whole first unit of the course, right? That was all about how radiative energy from the sun came to the earth, struck the earth, warmed the surface of the earth. The restless heaving ocean of air that mantled them both, oh my goodness, what a colorful expression, powered by the sun and twisted by the spinning earth beneath it. What is it talking about when it's saying that the heaving mantle of air is twisted by the spinning earth beneath it? What is it talking about? Something we learned in the second unit. Coriolis force, right, exactly. The atmosphere moved like a living, throbbing creature. Winds and currents pulsed through it. Gigantic columns of air billowed upwards for miles and sank again. What is it talking about when it's talking about these gigantic columns of air that are billowing upward? That's some feature of the general circulation. How about the ITCZ? A place where there are large amounts of air rising upward, and then they sink again. What parts of the world does the air that rises in the ITCZ, where does it sink?
Subtropical highs.
The subtropical highs, exactly. Absorbing moisture and releasing it. Well, we talked about moisture in the second unit of the course, and evaporation rates and condensation rates. Borrowing warmth from the tropics and carrying it forward. How is the atmosphere borrowing warmth in the tropics? Well, when cool air masses come to the south, warm heat from the ground, the sun warmed the ground warms up these air masses and warms them up. As they become a warm air mass now, and then they get sent back to the north, they are transporting heat from the tropics back up towards the poles. Breathing life wherever they touched. Above this endless activity, the turbulent air ocean becomes more placid. Well, because all this turbulent activity of the atmosphere that we've been talking about in this unit is all about the troposphere. Remember, everything that you and I call weather happens in the troposphere. Well, there's a whole lot of atmosphere up above it, but it gets to be much smoother, much less stormy. Up in the stratosphere, there's very little turbulence, there's very little winds, there's very little storm activity, etc. Oh, except for the raging rivers of the jet streams. Higher still, electrical charges swirled in the darkening sky, and meteors flashed in unbreathable gases blocked out all but a small slices of the sun's mighty radiance. My goodness, what a colorful expression. What is it talking about when it's talking about an unbreathable gas that blocks all but a small slice of the sun's radiance? It's talking about ozone. Right? Ozone up there in the stratosphere is blocking the ultraviolet radiation. Other gases up there are blocking other horrid things like gamma rays and so on. Pulled by lunar and solar tides, mixed with magnetic fields and ghostly interplanetary winds, the ocean of air gradually thinned away and disappeared upon the dark shore of space. Oh my goodness, what a colorful, well-written, strange thing to be appearing in what is actually a very, very stupid book. Anyway, I always find this little explanation here of description more accurately of general circulation. Kind of a fun thing to do on the day that we talk about the big picture. Sorry, I didn't realize I was on the screen there. one real theme in this unit of the course has been all about convergence and divergence. I've got the test ready, and I have to admit I didn't count or have the word count how many times convergence and divergence appeared. Most of us I do just for the shock and awe value of it. Oh my gosh, they appear 40 times on the test or something like that, okay? But convergence and divergence is a real theme. Practically every feature of the atmosphere that we talked about in this unit had either convergence or divergence, and of course it typically occurs in pairs. Something is air is converging at the surface, then it is diverging aloft, or is diverging at the surface and converging aloft. And of course that's associated with vertical motion. If air converges at the surface, there's really no place for the air to go but up. Can't go into the ground or anything. And then there will be upper level divergence when that rising air hits the tropopause. In the same sort of way, air that converges aloft, right under the tropopause, has really no place to go but down, hits the ground, and spreads out. So you can have divergence at the surface, but then you're going to have convergence aloft, or you can have convergence at the surface, but then you're going to have divergence aloft. And one could well imagine the many wonderful questions one could ask about this. There could be lots of questions of the form, where is there convergence in the ITCZ? And you would say that it's at the surface. Or we could have questions about, where is there divergence in the polar highs? Or is there convergence or divergence at the surface of the polar highs? You can write questions like that as part of studying, and you're probably guessing pretty well. I don't know if that's how you guys study, but when I was a college student, a large way of the way I studied was, well, I'm going to write questions and see what kind of questions I can come up with, okay? Pretty hard to come up with questions about some things. Some things were really easy, and you can kind of get a sense as to what they can ask, right? This is very askable. That's not really a real word, but you know what I'm saying. This is very askable stuff. Now, all along, we've been saying that this unit of the course is very visual. But to an outside observer who just wandered in, hadn't been to the class since the last test, and took the test, they wouldn't know that. The test does not look different than the other tests. It isn't like this test is 20 pages long because of all the pictures that are in there. Rather, this test looks like all the other ones. It doesn't mean that it isn't visual, it just means that the picture is in your head. So, for example, we have questions of the form, put the following features in order from north to south. Polar high, polar jet stream, subtropical jet stream, trade winds. Well, those are actually already in order, but you get the idea, right? You have to have a picture in your mind as to how this works. There isn't actually a picture there that you're labeling. That doesn't really work very well. It's hard to grade something like that. So, the picture needs to be in your mind. Now, obviously, you can write all over your test book, but I mean, once we verify that we've got one back from everybody, we just shred them. So, I mean, you're welcome to just draw all over it. That's fine. And so a lot of times I'd see when I flip through them that students have drawn the general circulation or something like that. And that's a really good strategy if that helps you. Let's pop over here for a second. Again, thinking about what the course is really about, we're talking about having different ways to explain and visualize things. We want to start with Hadley's original idea of the general circulation. Now, it's always hard to know how far to push it when the idea was wrong, but Hadley had some good ideas here, right? You can well imagine that there could be questions on the test that's about what did Hadley think, what made him think it should work this way, what aspects of this are right. I mean, he was right about things like warm air rising at the equator. He was right about cold air sinking at the poles. He was right about this general idea that there should be cells in the atmosphere, these closed circulation loops. But the real circulation required a lot more understanding of things like the Coriolis force and so on. And so we get diagrams like this. And there are lots of different ones of these that I've scanned on blue line. There are a couple of different ways that this is drawn in your textbook. You should be able to identify everything that's on here and explain why it's there. All right. Well, I'll take it back. Explain why it's there is a bit difficult. It was beyond the context of the course to be able to explain why there were doldrums. But at least